Welcome to Kitmasters University. If you're watching this video, you're looking for more information regarding fan clutches and Kitmasters fan clutch related products, and you've come to the right place. Our goal is to help you become a fan clutch expert, so let's get started. The primary purpose of the fan clutch is to provide cooling to the engine to prevent overheating and engine damage. Due to increasingly strict emission standards, engines have evolved to efficiently operate at high temperatures. However, excess engine heat is harmful to both the engine and its components. The engine cooling system is designed to allow the engine to reach its optimum operating temperature as quickly as possible and then maintain that temperature as evenly as possible. As the engine is running, chemical energy is transferred into heat energy, fuel into combustion. Some of the heat generated is used to operate the engine. Some of it is vented through the exhaust, and some of it is absorbed into the engine's core. It is the heat that is absorbed by the engine that can be problematic, and the cooling system exists to manage this heat. Surrounding the engine core are coolant passages where engine coolant, a mixture of water and antifreeze, flows through the engine. The excess heat in the engine core is transferred to the engine coolant and is pumped through the engine coolant passages. It is routed through the thermostat to the radiator. If the thermostat is closed, the coolant is not allowed into the radiator and it continues to circulate through the engine core. If the engine is operating within normal heat limits, this is all that needs to happen. Engine coolant collecting heat from the engine core is the initial and primary source of engine cooling. If the engine temperature rises above specified levels, the thermostat opens and allows the engine coolant to flow into the upper radiator rather than the lower radiator. After the coolant enters the upper radiator, it circulates downward through the radiator, which causes the heat contained in the engine coolant to dissipate to the ambient air. Airflow passing over the radiator assists dramatically in the transfer of heat from the engine coolant to the ambient air. The thermostat and radiator are the secondary source of cooling. If the engine coolant is still above specified levels, a thermo switch monitoring the engine coolant level will engage the engine's fan clutch. The fan clutch provides massive airflow through the radiator. The increased airflow reduces the temperature of the coolant as it passes through the radiator and aids in dissipating the heat directly in the engine. Once the coolant temperature is back within normal parameters, the fan clutch is turned off, the thermostat closes, and the first stage of the cooling cycle begins again. The fan clutch is the final stage of engine cooling. Because the fan clutch is the final stage of the cooling process, there is usually a 10 to 15 degree difference between the thermostat and the thermoswitch temperature setting. The goal is to have the radiator remove the heat before the fan clutch becomes necessary. Some of the primary factors that cause coolant temperature to rise above normal operating temperatures are lack of airflow across the radiator and engine. This can be caused by idle operation, low vehicle speed, plugged radiator. Excessive load on engine, which can be caused by climbing a steep grade, running PTO, hauling a heavy load, hot weather, poor engine coolant characteristics, insufficient radiator cooling caused by the radiator being plugged or restricted, leaks or low coolant levels. Now we will discuss the different types of fan clutches. Different fan clutch technologies are engineered specifically to operate in different classes of vehicles. All fan clutches rob horsepower from the engine in order to provide the airflow necessary for cooling the engine. This loss of horsepower is referred to as parasitic loss. Fan clutches are designed by application so they provide the required cooling while causing the minimum amount of parasitic loss. The following are the common fan clutch technologies. The electric fan clutch is designed for the passenger car and light-duty market. It operates basically the same as the electric fan in your house. When engaged, it requires very little horsepower draw and therefore only requires a compact motor to drive the fan blade. Electric fans are ideal for this application because they're very reliable and reasonably inexpensive. They are limited, however, in the size of the fan blade they can operate. Larger fan blades require higher horsepower electric motors. A high horsepower electric motor is impractical due to its size and cost. All pulley-driven fan clutches may be thought of as two components. One component that rotates with the pulley, called the drive portion, and the other half that independently rotates with the fan blade, called the driven or clutch portion. Some mechanism is used to get these two portions to rotate together in a coupled state. Once coupled, the fan blade rotates in the same speed as the pulley, and the fan clutch is engaged. This is true for on-off fan drives. With air-engaged fan clutches, it is air pressure driving the friction material into the fan plate. With spring-engaged fan clutches, it is spring pressure driving the friction material into the fan plate. An air-sensing viscous fan clutch replaces the spring, air, and friction combination with shear plates and viscous fluid to drive the two halves. Inside of the body of a viscous fan clutch, the drive portion and the clutch portion have shear plates. Shear plates are two independent plates that are lined with circular fins that interweave each other very closely but never actually touch, so there is no friction between the two halves. The center of the clutch has a reservoir which houses the silicone viscous fluid, a special fluid with a honey-like consistency which is designed to cause a shear force between the two halves. This shear force becomes the drive mechanism between the drive portion and the clutch portion. The air-sensing viscous drive fan clutch is a closed, self-contained system, which means it is not connected to a thermoswitch, to the ECM, or to an airline. It is completely self-contained. At the front of the fan clutch is a bimetallic strip or coil, which is made up of two pieces of metal bonded together with drastically different thermo-expansion properties. Small temperature changes equal large dimensional changes in the length of the bimetallic strip. The strip is connected to an internal valve, and the change in length of the strip causes it to either open and release the viscous fluid, or to close and contain the fluid in the reservoir. When the ambient air temperature rises, the bimetallic strip or coil expands and the valve is opened. This releases the viscous fluid. Centrifugal force causes the fluid to flow to the outside of the clutch housing and into the shear plates. As the fluid passes through the shear plates, it causes a shear action between the two portions, essentially filling the space between the shear plates, and a drag is created from the drive portion to the clutch portion. This causes the fan to turn. As the fluid is centrifugally forced to the outer diameter of the fan clutch, the force causes the fluid to enter a small fluid path that returns it to the reservoir in the center of the clutch, where it is then once again forced toward the outside of the clutch. This pumping action continues as long as the reservoir valve remains open. When the ambient air temperature reduces, the bimetallic strip or coil contracts, causing the reservoir valve to close. As the fluid is pumped into the reservoir, it is now contained. With no fluid in the shear plates to cause drag, the fan clutch is disengaged. There are many ways to increase or decrease the shearing action of a viscous fan clutch. Some examples are increasing or decreasing the amount of fluid in the clutch, increasing or decreasing the viscosity of the fluid, increasing or decreasing the number of fins on the shear plates. The pneumatic on-off fan clutch is designed for the heavy-duty vehicle market. It is typically an on-off fan clutch, meaning that when the fan clutch is in its on position, it is 100% engaged and rotating at the same speed as the pulley driving it. When it is in its off position, it is 100% off and the fan is freewheeling. As we have mentioned before, there are two major components to a fan clutch: the drive portion and the driven portion. The drive portion is connected to a pulley which rotates with the crankshaft via a belt. The driven portion is connected to the fan blade and freewheels when disengaged. Traditionally, a thermoswitch senses the engine coolant temperature, and when it rises above a specified level, it sends a signal to a solenoid valve to either start or stop airflow to the fan clutch, depending on how the fan clutch is designed. Once the clutch is engaged, it is 100% engaged. It provides substantial and immediate cooling to the engine and the engine coolant. Once the engine coolant is below the specified level, the thermo switch sends a signal to the solenoid valve to disengage the fan clutch. The pneumatic on-off is ideal for heavy-duty applications because it is generally strong enough to operate most fan blades required in this market. When it is in its off position, it is 100% off and causes no parasitic loss and creates no noise. The negatives to the pneumatic fan clutch are that it does require maintenance and it may be costly to replace or repair. There are generally two types of pneumatic on-off fan clutches: air-engaged and spring-engaged. In an air-engaged fan clutch, when the thermo switch senses that engine coolant is above the specified level, it sends current to the solenoid valve, which opens and releases air to the fan clutch. The air pressure travels through the body of the fan clutch and causes the friction plate that is attached to the fan blade to engage the pulley, which causes the pulley and the fan blade to rotate together. At this point, the fan clutch is engaged. When the thermo switch senses the engine coolant has returned to specified levels, it stops the current to the solenoid valve to shut off the air supply. Inside of the clutch, a spring will then push the friction plate away from the pulley and the fan clutch is disengaged. This is air engaged and spring disengaged. In a spring-engaged fan clutch, there is an internal spring that is always trying to engage the friction material. However, the internal spring is overcome by the air pressure supplied to the fan clutch. A spring is trying to engage the fan clutch, but air is holding the spring back while in the disengaged state. When the thermo switch senses the engine coolant is above specified levels, it sends current to the solenoid valve to shut off the air supply. With no air pressure to hold it back, the spring engages the friction material to the pulley and the fan blade rotates with the pulley and the fan clutch is engaged. When the thermo switch senses the engine coolant has returned to specified levels, it removes current from the solenoid valve to supply air to the fan clutch, which compresses the spring, which in turn disengages the fan clutch. This is spring engaged and air disengaged. The pneumatic two-speed fan clutch is designed with the heavy-duty vocational market in mind, but is also used in on-highway applications. A variant of the pneumatic on-off, the pneumatic two-speed is basically an on-off fan clutch with a mechanical attachment which causes the fan to rotate at low RPM even when the fan clutch is in the off position. Much of the cooling in heavy-duty over-the-road applications is provided by ram air. However, many heavy-duty applications do not have the luxury of the ram air that is typical in an on-highway application. Because of the lack of airflow across the radiator, the fan clutch may have to engage dramatically more often to keep the engine at optimal temperature. The fully engaged fan clutch causes more parasitic horsepower loss, which causes lower fuel mileage. Ideally, an on-off fan clutch in an on-highway application should only be in the on position less than 10% of the time. With this few number of engagements, it is typical for the fan clutch to last 4 to 6 years. In a vocational application, where there is low airflow across the radiator, the fan clutch might be in the on position as much as 50% of the time. Every engagement causes wear to the fan clutch, and each fan clutch has a limited number of engagements it is capable of in its lifetime. Over-engaging the fan clutch causes the end of life to happen sooner than expected. For these reasons, the industry has created the two-speed fan clutch. In a two-speed fan clutch, a mechanism, which varies by manufacturer, is placed on or within the on-off fan clutch. This mechanism will cause the fan blade to rotate between 15 and 40% of the pulley speed, even though the fan clutch is still in the off position. The airflow caused by the fan rotating at 15 to 40% is enough to keep the engine coolant temperature within specifications for a longer period of time. In other words, the airflow caused by the two-speed mechanism replicates the ram air enjoyed by on-highway vehicles and significantly reduces the number of required full engagements. The negative to a two-speed fan clutch is that it is more expensive than the on-off version. It may also make it difficult to develop cab heat in the winter. The two-speed mechanism itself requires little to no maintenance, but the same maintenance must be performed on its on-off base.